Mission's Hubble has filled a crucial observational gap. Its remarkable precision and stability have allowed it to function as an indispensable eye in the sky, unveiling the hidden dynamics and complexities of our solar system. One might assume that our moon would be a primary focus for Hubble, but due to its relatively large size in the sky, it cannot be fully captured by the telescope's imaging system. Instead, missions such as NASA's Lunar Reconnaissance Orbiter handle lunar imaging more effectively. Still, Hubble has contributed in indirect ways. During the 2012 transit of Venus across the Sun, scientists cleverly used the Moon as a reflective surface to analyze the event. By examining sunlight that had passed through Venus's atmosphere and bounced off the Moon, they were able to test techniques for identifying atmospheric compositions, methods that have since become essential in exoplanet research. This technique, based on how light is altered as it interacts with a planet's atmosphere, has laid the groundwork for identifying the makeup of worlds far beyond our solar system. Mars, in contrast to the Moon, is a more suitable subject for Hubble. It has repeatedly captured global views of the red planet, surface views often difficult to achieve with orbiters that only see narrow slices at a time. These full planet images provide invaluable insights into Martian weather patterns, seasonal transformations, atmospheric behavior, and massive dust storms. One particularly striking series of Hubble images showed a global dust storm engulfing Mars, rendering the surface completely obscured. Even amid this haze, Mars' tiny moons Phobos and Deimos were seen darting around the planet. Another time-lapse captured Phobos over a 22-minute span, showing its rapid motion in orbit. Phobos orbits Mars every 7.5 hours, making it the only moon in the solar system that completes an orbit faster than its planet rotates. These observations are more than visually captivating. They are critical to planning future missions, particularly those involving human explorers who must navigate and survive in these volatile environments. As our gaze shifts beyond Mars, we encounter the asteroid belt, a chaotic region filled with millions of rocky fragments. In 2019, Hubble observed an intriguing object within this belt, asteroid 6478 Gault. Despite its classification as an asteroid, Gault displayed two tails reminiscent of a comet. Scientists trace the cause of these tails to a phenomenon called the YORP effect, Yarkovsky-O'Keefe-Radzievsky-Paddock effect, in which uneven solar radiation gradually increases an asteroid's rotation rate. Gault, roughly 3.5 kilometers wide, now spins once every 2 hours, approaching the physical limit at which such a loosely bound rubble pile can remain intact. The rapid spin created centrifugal forces that ejected surface debris, forming the tails. Most asteroids are not solid monoliths, but loosely consolidated materials held together by weak gravity. Objects like Gault may ultimately disintegrate under their own spin. These findings highlight the ever-changing and dynamic nature of the asteroid belt, which is home to over a million objects larger than a kilometer in diameter, plus countless smaller fragments. Another fascinating Hubble discovery within the asteroid belt was P2010A2. Initially appearing to be a standard comet, its nucleus revealed something unexpected, an X-shaped debris pattern that didn't align with typical comet activity. Scientists concluded that this formation was the aftermath of a high-velocity collision between two asteroids. The resulting debris was flung outward in all directions, with some fragments later drawn back toward the center by gravity while others escaped into space. Such collisions, although rare, offer direct evidence of the violent processes that still sculpt our solar system. Though most asteroids follow relatively stable orbits, those that drift too close to massive planets like Jupiter can be thrown into chaotic paths. Jupiter, often dubbed the solar system's vacuum cleaner, exerts an immense gravitational pull that alters the orbits of many passing comets and asteroids. With a mass equaling nearly a third of all matter in the solar system outside the Sun, Jupiter's gravitational influence is unmatched. A dramatic example of this was the fate of comet Shoemaker, Levi 9 in 1994. The comet had been captured by Jupiter's gravity decades earlier, orbiting as a temporary moon. Eventually, it came too close and was torn into fragments by tidal forces. These fragments slammed into Jupiter's atmosphere at 60 kilometers per second, generating explosions with temperatures exceeding 23,000 Kelvin. One impact left a dark scar on the planet's surface nearly the size of Earth, releasing energy equivalent to 6 million megatons of TNT, over 600 times the power of all Earth's nuclear weapons combined. This event marked the first direct observation of a planetary collision and underscored Jupiter's role as a cosmic shield for the inner planets. Beyond gravity, Jupiter's magnetic field and radiation belts contribute to some of the most intense auroras in the solar system. Unlike Earth's auroras, which are sporadic and triggered by solar activity, Jupiter's are constant and hundreds of times more powerful. During NASA's Juno mission in 2016, Hubble monitored these auroras extensively, revealing that they are not solely influenced by solar winds. Instead, internal factors such as rotating magnetic fields and the motion of charged particles within Jupiter's magnetosphere play a major role. The result is a dazzling, unending display of polar lights unseen anywhere else in the solar system. Among Jupiter's many moons, Europa stands out as a potential haven for life. Beneath its icy shell lies a vast subsurface ocean, heated by tidal forces from Jupiter's gravity. While previous missions like Galileo and Voyager offered close-up images, Hubble made a groundbreaking discovery, detecting what may be plumes of water vapor erupting from Europa's surface. Observed in ultraviolet light, these plumes suggest that material from the Moon's ocean is vented into space, presenting a unique chance to study its subsurface waters without drilling through kilometers of ice. Hubble also detected sodium chloride, ordinary salt, on Europa's surface, indicating the ocean beneath might be chemically similar to Earth's oceans and raising the possibility of microbial life or prebiotic chemistry. Saturn II has remained a subject of close observation by Hubble, especially after the Cassini mission ended in 2017. Hubble has since become the primary tool for continuous monitoring of the ringed giant. It has captured spectacular images of Saturn's atmosphere, including vast storms that span thousands of kilometers. These observations are crucial for improving models of atmospheric dynamics not only on Saturn, but on gas giants in general, including exoplanets beyond our solar system. Hubble's long-term monitoring allows scientists to observe weather patterns and storm cycles, adding depth to our understanding of planetary behavior. Further out lie Uranus and Neptune, the solar system's icy giants. Since their only close-up came from Voyager 2 in the 1980s, Hubble's role has been vital in keeping tabs on them. It has documented seasonal atmospheric changes on Uranus, tracking cloud formations and storm activity. It also discovered Neptune's smallest known moon, Hippocamp, a tiny, 34-kilometer-wide body orbiting unusually close to Neptune's massive moon Triton. This proximity raised questions about how such a small moon could survive gravitational disruption, leading to new theories about moon formation and evolution in the outer solar system. As we move past Neptune into the Kuiper Belt, a vast, cold expanse filled with icy bodies and dwarf planets, Hubble's adaptability has again proven invaluable. One of its most significant contributions has been in the study of Pluto. Although discovered in 1930, Pluto remained a mere speck through ground-based telescopes. Hubble changed that by capturing the most detailed pre-New Horizons images of the dwarf planet, revealing bright and dark regions that hinted at surface complexity. It also discovered 4 of Pluto's 5 known moons, NYX, Hydra, Kerberos, and STYX, helping to map Pluto's dynamic and chaotic satellite system. This data proved crucial for planning New Horizons' 2015 flyby. Hubble also studied other major Kuiper Belt objects like Eris, Haumea, and Makemake, revealing their sizes, orbits, and surface compositions. Eris in particular was found to be nearly the same size as Pluto, possibly larger, depending on measurement methods, which prompted the redefinition of the term planet and Pluto's subsequent reclassification as a dwarf planet in 2006. In 2014, Hubble enabled another milestone by identifying 2014 MU69, later named Arrokoth, a tiny, 36 km object lying far beyond Pluto. Its detection allowed New Horizons to extend its mission beyond Pluto. In 2019, the spacecraft conducted the most distant flyby ever, revealing Arrokoth's dual-lobed shape and reddish hue. These features indicated a gentle formation process and accretion of small bodies rather than violent impacts, offering rare insight into early solar system development. Beyond objects themselves, Hubble has also helped investigate the environments they occupy, including interactions between the solar wind and planetary magnetospheres, contributing to our understanding of the heliosphere, the vast bubble created by the Sun's magnetic field that surrounds all planets. Its studies of moons like Enceladus, though limited by distance, complement data from the Cassini mission. Hubble's ultraviolet observations suggest water vapor plumes erupt from Enceladus' surface, hinting at subsurface oceans that may harbor conditions for life. In all these ways, Hubble has gone far beyond its original mandate, transforming our understanding of the solar system and showing that even in the space closest to home, the universe is full of mysteries waiting to be explored. In addition to its extensive observations of known solar system bodies, the Hubble Space Telescope has also provided critical support in tracking transient and unpredictable events, including the passage of comets and the sudden appearance of new impact sites. For instance, in 2009, Hubble detected a dark scar on Jupiter's atmosphere reminiscent of the Shoemaker-Levy 9 collision. This previously unrecorded impact likely resulted from an asteroid or comet crashing into the planet, underscoring the importance of continuous monitoring. Such sudden phenomena offer rare opportunities to study planetary defense and the behavior of celestial impacts in real time. Similarly, Hubble has observed numerous comets both within and beyond the orbit of Mars. Its ability to capture ultraviolet and visible light has enabled scientists to study the chemical composition of cometary tails, revealing the presence of water ice, carbon compounds, and even organic molecules. These observations have profound implications for understanding the delivery of water and life-forming elements to Earth, and potentially to other worlds. Hubble's continued relevance lies in its capacity to pivot between scheduled observations and urgent requests to capture unexpected celestial phenomena. This flexibility has allowed it to study eclipses, occultations, and transient plumes, events that require rapid coordination and